Hi, everyone. Yeah, I am Alowolodu Olufunso Dayo from Federal University of Technology, Akure, Nigeria. And I'm so glad to be here. And I've had an amazing time so far, and I hope you have too. I'll be talking on bridging IoT and machine learning with Python for sustainable agriculture. My co-presenter, that's Dr. Iyinoluwa Oyelade is unavoidably absent because of some unforeseen circumstances. She sends her regards. Okay, so agriculture represents a crucial sector that underpins our population growth and well-being. It has been providing nourishment for generations, and according to the United Nations, agricultural development is one of the most powerful tools to combat extreme poverty and boost prosperity and feed the global nation. Meet Madam Alice, a maize farmer in northern Nigeria. Every planting season, she faced the same struggle, like unpredictable rainfall, worsening drought, and so many other things amidst insecurity. Now, without reliable data, she either planted her crops too early or too late and missed the optimal growing season. And each failed harvest pushed her further into financial hardship. And this has made us to discover that our current methods of food production, including monocropping and intensive tilling, have degraded over 1/3 of the world's productive topsoil while failing to provide the agricultural yields that is necessary to sustain the growing global population. For instance, over 280 million people in Africa, they suffer from food insecurity with climate change and inefficient farming practices, thereby worsening the crisis. Nigeria, in particular, where I came from, has over 25 million people facing food insecurity with unpredictable rainfall, desertification, and rising costs, making farming increasingly difficult. Now, food insecurity affects millions, particularly in Africa, where agriculture faces severe productivity and sustainability challenges. One of which is climate change and poor resource management amidst socio-economic factors. All this contributes to the problem facing agriculture. And as we all know that agriculture is highly dependent on climate and weather conditions. So prolonged drought or extensive rainfall can have devastating effects or devastating repercussions on soil health and fertility. And it's been predicted that average global crop yields for maize, they are projected to drop by 24% in the next 60 years. And as we all know that maize is a crucial staple food that is grown mostly all over the world, but the largest quantities are produced in nations near the equator, including North and Central America, West Africa, Central Asia, Brazil, and China. Now, by the end of this season, we're going to cultivate some IoT knowledge and machine learning data, using machine learning models. And I hope that our harvest of data will help us make more informed decisions. So we're going to see how IoT devices collect agricultural data from sensors. We want to see how to process and analyze IoT data using Python libraries like Pandas, NumPy, and the SciPy. We'll explore machine learning applications in agriculture using TensorFlow, PyTorch, and the scikit-learn. gain insights into decision-making strategies for irrigation, pest control, and yield prediction. Then we're going to see real-world Python code demonstrations to build a complete smart farming pipeline. Now, the role of technology using IoT and Python-driven machine learning. Now, assuming that we have been introduced to IoT, and Madam Alice, that I first pointed out to us, started using an IoT-based soil moisture sensor system that is powered by Python, sorry. Now, with real-time data on soil conditions and automated alerts on weather changes, the madam knows exactly when to plant and to irrigate her plants. This can possibly make her yield to increase by 35%, and she no longer wastes resources on unnecessary watering and planting as at when due. So, the integration of IoT and machine learning powered by Python is revolutionizing agriculture, and this enables farmers to make data-driven decisions, because we all know that traditional farming relies on manual observations and intuition, which can be inaccurate and inefficient. However, smart farming leverages technology to optimize every aspect of the agricultural process. How can Python-driven machine learning enhances decision-making? We talk of predictive analysis, whereby AI models forecast weather patterns, disease outbreaks, and even optimal harvest times. The algorithms can analyze sensor data to determine when and how much water the crop needs. And with image recognition and anomaly detection, this can help identify early signs of infestation, because that is one of the prevalent challenges of agriculture, especially in Nigeria, infestation. And with historical and real-time data-trained models, it can help estimate expected harvest, hereby aiding supply chain. And machine learning models can suggest actions based on patterns, hereby improving efficiency. When we look at the role of IoT in agriculture, we talk of real-time data collection, automated alerts, precision farming, remote monitoring, whereby farmers can access farm conditions from anywhere via mobile apps or dashboards. Now, the Internet of Things in agriculture refers to the use of connected sensors and devices that collect real-time data to help farmers make informed decisions. And this has helped them by leveraging IoT. Agriculture becomes more precise, efficient, and sustainable. And these are the types of sensors that are used in agriculture. We talk of the soil sensor that measures the soil components like the humidity, the temperature, the pH value of the soil, and so on. And even the nutrients like the nitrogen, the phosphorus, the potassium that are present in the soil that aids plant germination. Then we talk of weather sensors. These are used to measure the atmospheric condition in order to help make informed decisions, to know when to farm, when to plant, and when to harvest. And you talk of crop health sensors, livestock monitoring sensors, and even automated irrigation systems. Let's look at the power of Python in agriculture. Python is the ideal programming language for smart farming due to its extensive ecosystem of data science and machine learning libraries. With Pandas, NumPy, and SciPy, data can be cleaned and analyzed, while TensorFlow, PyTorch, and scikit-learn enables predictive modeling and automation. Python also allows easy integration with IoT platforms like the Raspberry Pi. I saw that some people, they wanted to auction the Raspberry Pi yesterday, and I was really hoping I could, be the lucky winner. So Python allows easy integration with all these IoT platforms and even cloud services, hereby making smart farming accessible and scalable. Now, to properly understand how to bridge IoT and machine learning using Python, we'll consider a case study project titled Maize Yield Prediction using IoT and machine learning techniques. And the main objective of this project is to develop a maize yield prediction model using machine learning algorithms. Here is our farm. The picture you are seeing there is a colleague of mine, Dr. Olayinka, who is also a lecturer in Wellspring University, Nigeria. For her PhD project, she tried to collect data. And what she did was that she was able to get a plot of land, divided the land into three different portions, of which different species of maize were planted with different soil components, in the sense that a portion of the land was used as a control section, whereby the land was just bare like that, no addition of fertilizers, no addition of manure or anything of sort. Another portion of the land was, introduced. Manure was introduced into the land. Another one with fertilizer. So we developed an IoT sensor-based microcontroller system with API functionalities, and the system is used to collect real-time data from the experimental farm from the planting to harvesting period that lasted for 75 days. And data collected from the farm include soil parameters like the soil pH, soil temperature, humidity, the nitrogen, phosphorus, potassium, and even atmospheric, and also some atmospheric parameters. We're talking about the temperature and humidity of the atmosphere at that time. And the logging system incorporates an API to collect real-time data from the open weather site. And throughout the experimental period, spanning 75 days, this data was collected on a daily basis. And I don't know if time will permit me for us to see the sample data that was collected. It started from day 0 that the maize were planted. And so the IoT data set is made by Africa, and it is for Africa. Because the major problem we have is in Africa is when we use standardized data set that is collected internationally or from another place, we are now using it to solve our problem. We are forgetting the fact that we don't have the same weather condition, we don't have the same soil texture. And if in a bid for us to use the internationally sourced data set to solve our own problem, then we are not getting the optimal result. But I'm happy to tell you that this data set is a locally sourced data set by Africa and for Africa. So we have the soil environmental data, we have the physical data that daily measures the maize growth, right from the day of planting even till the day of harvest. Then we took the yield data that measured and compute post-harvest yield data. Now, this is the sample of the yield data set that was collected. And these are the Python libraries that were used for our for our data analysis and manipulations. So we used Pandas, we used NumPy, we used Matplotlib, the Seaborn, and some other libraries. So after we have collected our data, remember I told you that we have 3 major data sets, ranging from the soil data to the environmental data and the physical data. So we match these data sets, and we have 189,729 rows and 58 columns. That is, the attributes are 58. And we need to remove the irrelevant features. So after we have removed the irrelevant features, then we are now left with what we have there. So what we did was we did manual dropping of unwanted columns like the serial number, the ID, the plot number, the features that has nothing to do with the yield at the end of the day. Then after that, we now had to split the data set. After we split the data set into feature sets, that is the X variable and the target variable. Remember, the target variable is the yield at the end of the day. Then we now need to exclude the non-numeric features from the numeric features for feature conversion. Then we convert the non-numeric features to numeric features using that code snippet that we have there. Then, of course, we know there will always be missing values, and we had to use the mean imputation for our missing values. Now, we now look at our data exploration, as this step is needed to see the relationship of each feature with the target label, that is the yield data. So we had to use box plot to identify the relationship between the categorical data with the target label. So this code snippet interacts through a list of categorical features and generates a series of box plots, which is what we have, part of what we have here. So the topmost left box plot represent different categories or levels of conditions or operations that are treated as discrete values. And then the x-axis, which is the total grain yield, represent the amount of grain yield in kilogram. At the end of the day, the box plot shows the distribution of the total grain yield for each category of the condition, that is the atmospheric condition at that particular time. Then we use scattered plots to identify the relationship of the continuous data with the target label. Then we look at the features using Pearson correlation. So this shows how correlated the features are with the target variable. So the red colors in the heat map, shows positive correlation, while the blue colors in the heat map shows a negative correlation. So we now go further to see the importance of each feature to the target label using the information from the Pearson correlation method. So the top features have the longest bars indicate the strongest absolute correlation with the total grain yield. So these features, they are likely to be the important predictor in a linear model, in this case, the total grain yield. And the total post-harvest. We could see that the total grain yield, the total post-harvest of the maize with and without husk, they are important in our prediction. So we now need to select our features. And choice of feature selection depends on so many factors. We talk of the data size, we talk of the feature interaction, and then the model type. So for this, we use the select k-base with F regression, with mutual information regression, and the RFE feature selector with ridge estimator. So these are the code snippets of the feature selection algorithms. So then we now have to show the ranking of the top 10 features that are selected by our feature selection algorithms. So these are the top 10 ranked features. We have the total grain yield, total post-harvest, corn cob with husk, and so on and so forth. So this one is the ranking features for mutual information, as we have depicted. Then the one for RFE, these are the top features. We decided to use the three different feature selection algorithms in order to be able to match the best features for our prediction, because they've already, the essence of this is that we want to really prove that the data collected for Africa really works for Africa. So we now try to predict the yield, the total yield, using the data that has been collected and compare with what was really the actual total yield at the end of the day. So we now used 3 machine learning models. That is, four. We have the XGBoost, we have the multi-layer perceptron, the k-nearest neighbor, and the Bayesian regressor. So we trained each feature set on these machine learning models to see how well the features perform on the models. And at the end of the day, the models were evaluated using these 3 model evaluation algorithm. That is the mean absolute error, the R root mean squared error, and the R squared score. At the end of the day, this is the result based on the feature selection algorithm as trained on the machine learning models. So we could see that the models, they achieved very high accuracy with R2 score values close to 1. The XGBoost, the KNN, and the Bayesian regressor, when combined with the select k-based or the mutual information selection, they achieved an R2 score of 1, whereby the multi-layer perceptron generally showed a slightly lower R2 score of 0.99. So the XGBoost with the select k-based features generally performs better, because when we compared the predicted values with the actual value that was realized after the post-harvest, we could see that XGBoost with select k-based features, they generally performed better. That is, they make more accurate prediction than the k-nearest neighbor model with the RFE features for this particular task and this dataset. Because you could see that the points are more tightly clustered around the around the prediction line. The KNN model with RFE shows more variability in its predictions, and it tends to have larger prediction errors for some instances. So on this note, we could see that integration of IoT collected agricultural data with Python-based machine learning techniques, employing algorithms like the XGBoost, the MLP, KNN, and the Bayesian regressor, enables highly accurate maize yield prediction. And the feature selection methods used further optimize model performance, demonstrating the significant potential of this approach can produce accurate maize yield prediction, improved farm management decisions, and sustainable agricultural practices. Moreover, it provides a scalable framework for future smart farming systems, especially in developing regions. So these are my references, and thank you for listening.
So the columns that were highly correlated, the post-harvest, maybe it was the weight or something, I can't remember what those two columns are called. But would you ever know the values of those columns before you have an estimate of what the yield is going to be?
No, we never did. All we just did was that after we have performed our evaluation, we now compared to the total post-harvest yield, just to be objective in our evaluation.
I guess wouldn't that be the equivalent of you have a picture of a bunch of vehicles and one column is the number of airplanes and the other column is the number of cars? Are they too highly correlated where they're essentially measuring components of the same thing?
Yeah, I think so, yeah.
Okay, cool.
Thank you.
Thanks for the talk. I'm just curious what your plans may be, if you have plans for next steps in making this data available for people to use in farming in Africa, and also what additional data collection you're considering in the future, maybe to get more granular data for different regions, that kind of thing.
Yeah, thank you. The data is publicly available. Here, let me see. I shared here. That's the third and the fourth reference. Yeah. So the data is publicly available.
Great. And any next project?
Yeah. Now that we have ascertained the versatility of the project, we intend to take it to other regions of Nigeria first before moving to Africa. And West Africa, specifically, we have almost the same weather condition and possibly soil texture. I've not really traveled extensively across other African countries, but I've been to Ghana, and I know it's just as if I'm in Nigeria. So I'm sure what works for Nigeria will definitely work for other African nations.
Thank you.
Thank you.
Hello, thank you for the presentation. I had two questions. The first was about the sensors themselves. So was there a separate effort to choose and select which sensors ultimately went into the experiment? And if so, or if not, is there a plan to repeat the experiment with different sensors or different components, or will this be the model moving forward as you expand to other regions?
Yeah, there are sensors that are used for agriculture. We have the soil sensor, like I've said, that measured various components like the soil texture, the pH value, the nutrients in the soil, the temperature, so there are some sensors that combined all these sensors together, and there are some that are just separate like that. So it depends on your choice. You can use any sensor you want in as much as it gets you what you desired. And the second question, please.
Sorry, thank you. And then my second question is, maybe it's too far ahead, but if a farmer wanted to implement this system, do you have any idea what the lifetime of that system would be, how frequently they'd have to replace these sensors, or what that effort might look like?
Oh, well, we have not looked far ahead into that area, but we believe the sensors will be replaced as the need arises, because you can't, in as much as it's still giving us what we want, then what's the point replacing them? In as much as it's not as if there's if there's no adverse condition to the sensors, then I don't think there's need for us for constant replacement. But they are being constantly monitored, to check for any need for replacement. Yeah.
Got it. Thank you so much.
You're welcome.
Hello.
Hi.
So I just wanted to give a quick compliment, actually. So I'm a data analyst, and I feel like my job primarily is focused on providing information to others and to help people make informed decisions. So what I really liked about your talk is it feels like you're trying to help people. And I think that's one of the cool things about Python. So I just want to give that compliment of thank you for leading by example. I think your talk was very inspirational. So thank you.
Thank you. Yeah.